Okay, so let me go ahead and get started. So, like I say, I have about 5 problems that he sent me. Some of them I'll go over fully, others I'll just do part of them, and then others I'll just kind of give you the main idea behind it, and then you can look at his explanation later. So this one is pretty geometric. So basically what it says is we have 3 stars, one here, one here, one here. Is it showing up okay? Oh, wait. Sorry about that. Okay. So one here, and one here. And basically they're, I think, going in a circle. And we want to find basically the velocity of each star and then the time period it takes for them to go in the full circle. So what he does first is we need to find the force that each star is exerting on, the other star. And so they all 3 stars, we're just going to say they each have the same mass, and this is the mass that they have. So the forces are going to be the same, and we calculate the force using, let me see. The mass of 1, I'll just put it this way, and then the mass of 2, and then the radius squared. That's that general formula that we all know for gravity. So basically, we just need to plug in some things. So that's actually going to be, so let's see, so we'll set this equal to the force between A and C, which is the same as the force between, the force between all of them. And we're going to plug in numbers in a second. So B and C, and then A and B. And we can just call that F prime because it's going to be the same thing. So we just plug in the numbers. And actually right here, what he does is he uses, let me actually copy what he uses. It'll take me a while to write it down. So he uses this formula, which kind of seems out of nowhere, but after looking at it, it actually comes from the law of cosines. That's how you get that. So let's see. I don't know if I want to derive this. So basically, let me label this. So this is an equilateral triangle. So each angle is of measure 60. And so that's where you get that part. If we look up the law of cosines, let me look it up really quickly, because I did this last night. Actually, let me not look it up. Let me write it down. So let me write it from memory. So law of cosines. Let's see. So let me see. I will aim so that. And sorry for my tiny writing.
Are you gonna upload it?
Yes.
Okay.
Yeah.
Writing doesn't matter.
Okay. Yeah. And I'm recording this anyway. So
Okay.
let's say this is small a, this is small b, and this is small c. So then the law of cosines is going to be So let's see, I think it's, let me see. So it's basically a squared plus b squared. So the law of cosines with respect to basically this type of angle. So you have a squared plus b squared minus 2ac, and then cosine of the angle opposite them. So, or I'm sorry, AB, and then cosine the angle opposite of those. So that's going to be capital C. And so that's where he gets that. So all of these have measured 60. And so that's how he calculates the force between them. And let me show it up here to make sure I have it right. This one. And they go through some derivations. This one's kind of interesting. Apparently, you can kind of derive it based on the dot product, and that's kind of where you get. So with dot product, it's the magnitude of one times the magnitude of other times the cosine of the angle between them. So that makes it kind of easy to remember. And so he has. So basically, c squared. So this point right here is a square root of all this stuff. And so that's how he ends up getting this. And so he plugs in the numbers, let's see, or he sets that equal to, let's see, I need to remember. Let me see, hang on. So this is going to be that. Let's see, how do I want to do this? There we go. So basically he adds this, so he squares this. It would take me a while to write this, but he squares this part, that's this. Then he adds, so this squared is equal to that squared, or this is equal to that squared. This is equal to that squared. And because these two are equal anyway, this is going to be 2 times that squared. And then cosine of 60, if you remember from your, yeah, I think you got, yeah. Say it again. Yeah. And I always like to draw the special triangle just to make sure. So, you have, if this is x, then this is 2x, and then this is x times the square root of 3. And so, let's see, cosine of 60 is actually going to be, let me see what I get wrong here. Okay, it's 1/2. I'm sorry. So cosine of 60 is 1/2. So you plug that in here, that cancels with the 2 here, and then basically you have this being added to itself 3 times. Then you take the square root of that, or let's see, this squared being added to itself 3 times. So you take the square root of that, and then you have this part. But then you multiply that by not 3, but the square root of 3. And that's how you end up getting that part. And by the way, I forgot to do this, but the R in this case is A. That's how he labels it in the diagram. Let me see.
What is
Where?
that? Law of cosines?
Yes.
Okay.
Yeah. Oh, let me erase that.
Oh.
Yeah, so this is the distance between the 2 stars, which is A all the way around. Excuse me, A all the way around. And so I can go ahead and just plug that in there instead. And that's how he gets. So just to kind of confirm, here is where we are right now. So this formula here is basically the same. And I can further simplify this by saying, okay, the masses are equal. I don't really need this subscript here. So I'm just going to erase it. And I can really just square it, but he just leaves it in this form, having G, M, M, and then over A squared, G, M, M, over A squared times the square root of 3. Bless you. So that's where we are right now. And then he finds the, yes.
Is it A squared or R squared?
Well, so what I did, since he labels it in the picture, because we're trying to find the force between these two.
Yeah.
And so, you know, it's this, the mass of one, the mass of the other, the distance between them squared. So that's that, bless you. And then you multiply it by the constant, the gravitational constant. Okay, so that's that. So let me, at this point, let me copy and erase some stuff. All right. Oh, this. Okay. We'll just leave that. Now again, we use, so now we need to find this distance here because we need radius. Actually, let me see, let me leave something up here. So let me go ahead and leave this up here. All right, now we need to find the radius. And again, we have to use some geometry, so R is the radius in this case. So we've got A here, and let me see, which one do I want to use? Okay, let's use this triangle, that'll work. There are different ways you could approach this. Like I said, I kind of had to look over this myself to figure out what exactly is going on. So here, you can't really tell in the picture, but the picture is not exactly to scale. But this line segment here bisects 60. And if you don't believe me, well, it's going to the center. This line is going to the center, and then over here, it's the same distance you could say from this star to this one, because it's supposed to be an equilateral triangle. So this angle here is supposed to be 30 degrees. And so we can use that, and of course this is going to be right triangle. So now we have the 30, 60, 90 triangle again, so that's good. And so we're trying to find the hypotenuse, R. So let me see, let me reconstruct this over here. So we have R here. We know what A is, which is from here to here. So this right here, which is right here, is going to be half of that. And then this one, we don't know, but that's fine. We don't need to know that. So this is going to be 30. And so if this is, so let's see, let me do this. Let me get rid of this. So if this is A2, and again, just kind of use this for reference, then this is going to be whatever this is divided by square root of 3. So let's see, how do I want to do that? A squared times square root of 3. And then you just multiply that by 2 to get from here to here. So then that's going to be just A times square root of 3. And then that's how you get that. And hang on, let me make sure I did this right. Oh, I'm sorry, I said divide. Hang on. So it's divided by 1, so it's divided by square root of 3. And then this one, the 1/2 cancels and you just have A divided by the square root of 3. And that ends up being what R is. So there we go. Does that kind of make sense? Like I say, it's just kind of playing around with the ratios in the 30, 60, 90 triangle. So that's how you end up getting that. And just to confirm, that's what he has at this point. And by the way, we're going to use this because we need to find the velocity. So basically, it's a centrifugal force that is equal to the force attracting the stars together. That's kind of keeping them in balance. So you set those equal. So let me go ahead and copy this. All right, so we know everything. Let's see, so we're trying to find the velocity. So there are a couple of things we can cancel here. So let me use this. Mass is here, we can go ahead and cancel. Let's see, let's go ahead and multiply both sides by R. And then let's see. We got the velocity squared. Hang on, let me make sure I have this right. Let me plug this in, hang on. I don't want the square root of a square root. So yeah, let me go back. Okay, so the whole purpose of finding R is to plug it in here. So, and fortunately, the square root of 3 cancels in this case. So we have A over square root of 3. And like I say, at this point, it's all just algebraic manipulation. Like we had the geometric manipulation a second ago. Let me rewrite this part. Let's just put squared. A squared. Then from there, let me rewrite this part. Say it again. Oh, okay. All right, so from here, let me cancel. And again, sorry for the small writing. So let's see. Fortunately, square root of 3 goes away. We don't have to fool with that. 1a goes away, so we don't have to worry about that. 1m goes away. We don't have to worry about that. Oops. And then we're just left with v squared equals g, and then 1m over 1a. And then if we take the square root, we get gm over a. And when you plug in the numbers, which I'm not going to do because this has kind of been going on longer than I wanted to. But when you plug in the numbers, that's what you'll get. You'll get the answer. And then it asks for the time period. And that's going to be the distance traveled divided by the velocity. So let me go ahead and copy this. The second part is not as long as the other one. Yeah. All right. I just got rid of this part. Okay. And the time period is measured in seconds, just to kind of confirm that this is right. I'll just go ahead and use units. Or, well, I'll just work out the units. So, here it's going to have to be the distance traveled is in meters, velocity is in meters per second, meters cancel, and then you just get, let me write it this way. So 1 over seconds over second, or 1 over seconds is seconds over 1, and then all that cancels, and then you just get seconds. So a little bit more elaborate, but basically you just plug in all of this. So the distance traveled all the way to make one cycle. In cycle divided by the velocity. And then the distance traveled all the way around is, so we have R here, it's basically just 2 pi R, and then the velocity, you can just say V. And then basically, we know what V is, we know what R is, you just plug in those numbers, and that's what you get. And that's actually kind of as far as he goes, because you can plug in numbers at that point. So there we go. So there's the first one. I took a little longer than I wanted to. Are there any questions over what I went over? Like I say, it gets a little weird with the geometric manipulation and all that. It's like you have Euclidean geometry going on here. So I don't really know, actually. These are the problems he sent me. Now, they're not necessarily over everything we just went over, but yes, and you have another question? You had a question?
Yeah, will we receive the slideshow later on?
Yes, yeah. So you'll be able to, for instance, read his very long explanation on part E of this, which I'm not going to go over. So it's this and that. So yeah. Oh, and this one, let's go ahead and go over this one. I'm just going to sketch out. Yes. Yeah, I talked to Dr. Bolton about that. I think we're just going to, So when okay, actually, first, before I mention that, I'm going to try to send out an email like I did a couple months ago or something like that, where I said, okay, this is your grade for exam 1, homework 1, exam 2, homework 2. Just take out 20%. So when you're calculating labs, if you have that, instead of it being out of, say, 1,000 points, just make it out of 100. So hopefully the labs are graded that way. So final is actually, no, so the final, which also doubles as test 4, is basically not going to exist. It's just going to be test 4. You know what I mean? Yes. Yeah. So basically that 20% disappears. So instead of out of 1,000% or whatever, it is now going to be remove the 200%, 800%. So when you're calculating your grades of kind of where you are, just throw out that, and then, you know, you can throw in some kind of X for the final, some kind of value for the final, you know, just plugging in numbers, and just divide all that by 800%. And I can maybe go over an example after this. Mm-hmm. Any other questions? Good question. Good questions, actually. Okay. So yeah, let me sketch this one out, because I'm just going to sketch it out. Let's go ahead and take a copy of this picture. Like I say, for this one, he goes over, he has a pretty good explanation. So let's copy all that and paste. And copy this. Get rid of this and paste it. Okay, there we go. Let me actually make this bigger. I'm just going to label the forces and just leave you at that. Leave you with that. And this should not take long. It should not. I mean, I say that, but we'll see. I tend to be a little over thorough. Apparently, it's something I can't help, because I tried and it doesn't do anything. All right. Move this over. Okay. So we have the center of mass here of a ladder. And basically, what we're asking is this guy is climbing up the ladder, and at some point is going to slip out from under him. And we want to know, okay, at what point is that going to happen? So we need to use several equations. But first, we have to find the forces so we can know how many equations we need. We know that we're going to need, just kind of looking ahead, we know that we're going to need we can, you know, sum the vertical forces and the horizontal forces. We can do that. So we at least have 2 equations. If we need more, we'll see. So just to label the forces, so we have the weight of the ladder, and that's going to be right here at the center of its mass, which is already labeled for us. Let me go ahead and call that force 1. Then we have him, his force, so we'll go ahead and call that force 2. And then we have, so it says in the problem that the wall doesn't have any friction, so it's not going to prevent this ladder from sliding at all. But it is exerting some kind of force, because if it weren't, then it would be like there's nothing there, and, you know, this would fall over. And it's really exerting kind of a normal force. So let me label that as F3. And the same at the bottom here. So we have a normal force. F4 we'll call. However, here it says that the lower end of the ladder is on a flat surface where the coefficient of static friction is, this given. So that means that it is going to resist using friction. So while this is trying to go out this way, the floor is exerting, a force on it, which I will call F5. So let me go ahead and label label all of these. So F1 is going to be, so we'll find, we'll just calculate formulas for these. So this is basically the gravitational force. And how do I find that? If I know the mass of the ladder is m, how do I find F1? So force is mass times acceleration. What is my acceleration of the ladder? Yeah, there we go. Yeah. G, I'll just say G. I'm just going to use letters, but yes, that is right. So we'll say mg. And then F2, so that's going to be this one. Same thing. We say for some reason that it's, perfectly 2 more than that, so it's just going to be, which is good because we don't have to worry about too many variables. So we have 2m times g. And then, let's see, for F3, it's going to be a normal force. So we're just going to label that. What he does is he just labels it as in subscript with a W, I'll just say wall, which is going to be the normal force of wall. Then we've got F4, same thing. How we notate it, normal force of floor. And then here, how do we find the, so F5, how do we find the force of the frictional force? Anybody know? So it's going to use this, the coefficient. So I am going to use something here as well, one of these variables that I already have here. So let me go ahead and, so it's going to be that multiplied by, anyone? What is it? What, that I multiply by? Yes, that's right. So it's going to be this one, of course, yeah. Oops. All right. So I have 1, 2, 3, let's see, 3 unknowns. Now, for some reason, he uses this mass M as capital M. I'm not quite sure because you could just plug in this. But I'll just, for the sake of completion, or for the sake of, just kind of matching up things, I'll go ahead and add this on here. And so the equations, let's go ahead and write it in this. Equations to use, so we can use the sum of the vertical forces, set that equal to, equilibrium, we have the sum of the horizontal forces. So those are two easy ones. And then, let's see, let me make sure I have this. And then another one that we could use, and let's see, how do I want to put this? Let me use this color. We can use torque, the sum of the torques, excuse me, we can set that equal to 0. So what he recommends is just put the axis here, so you don't have to worry about F5 or F4, you know, those can kind of go away, and then you just have some of these torques, or the sum of those torques. So the sum of the torques about, we'll call it point, I guess, A, right there. Point A. And you can use any reference point. That just makes the calculation a little easier. And then let's see. We got 1, 2, 3, 4. And then the fourth equation that he uses, and at some point he introduces an x variable. Let me see, where's the x variable? Okay. And I might just leave you all to look up that, because I'm not sure where that comes in. But the fourth equation that he uses is that the static force, so at the point that, so we're considering the point right before the ladder starts to slip. So we could say static friction. Oh, no, wait, no, that's not what it is. Let's see. So he uses F of S, which I think is the force of the student. Let me see. And that's going to be equal mu of S times N of F. Okay, now with respect to our diagram, so that's what is on his, but for us, F of S in this case is actually F of 5, which is kind of unfortunate. Let me see if I can draw this right. So F of 5, because I don't want it to look like an S. And that equals mu of S times Actually, let's make that capital because that's how I had them. Times mu of, or times f of 4. So those are kind of the equations. And like I said, he goes over it in a little more detail than I will. So basically, it's just finding the variables and then finding out which equations you need. So you can use the vertical forces, horizontal, and the torques is what you can use. So any questions on that? I know I was kind of all over the place with that one. Let's see. Let's go to this one and see if I can make it a little shorter. So this one is only one slide, so let's see how I do. All right. Now, the only thing in this one that confused me, and it's probably in your book somewhere, is, so we know that the, let's see. Okay, that's acceleration. That's not. Okay. I just instantly got it. Okay, so let me actually go through it a little bit. Okay, so force equals mass. Let's say force due to gravity is mass times acceleration, which I am just going to call g. All right. Bless you. Okay, what also is force due to gravity? Well, we'll just use that formula that we've been using. Let's see, how do I want to notate this? So m, let me define, let's see. Let m, so lowercase m equal the mass of some person, you know, of the person on the earth. And then let capital M equal the mass of Earth. Okay. So let me plug in those because we know we have the mass of the first one times the mass of the second one, and then we take the distance between them and square it and divide this part by that. You know, that's standard stuff. Now, here's what was confusing me. Why the form or the formula that he uses is not this. It's actually something different, and I just realized how he derives it. So let me set this expression equal to this expression, and I'll show you. This may be obvious to you all, but when I was looking over it last night, I did not get it. I was just going to take it as given. So you have this one, this one. Oh. Squared. Now, very simple. It's very simple. I don't know why I didn't realize this at first. Cancel and cancel. And then you're just left with, we're finding acceleration. We're not finding force. That's what I didn't get last night. So you just have this. And so if you look at his PowerPoint, he uses that. So that's an acceleration. And then we can adjust it because basically we'll have to use some algebraic manipulation here a little bit. So basically, So acceleration due to gravity varies based on how high you are from the center of the Earth. And so we estimate that, okay, we want gravity to be, 70% of what it usually is at the Earth's surface. And then, we're just going to say the distance from the Earth's surface is the radius of the Earth. And let me actually write that here. So radius of Earth. Now let me see, I want to go up to a height of h. So that's going to be the radius, or that height is really going to be, or the distance from the center of the mass of Earth is going to be the radius plus whatever height I want to go to. Let's see what I want to call that. Distance from Earth center. And we can just modify this one, so that's what he actually does. So instead of r squared, modify it, r plus h squared. And let's see how do I want to notate that. So that's going to be the force at height h, and then define the gravity at height h. Copy, paste. And get rid of that. And there we go. So we already know, so let me see. So again, I'm going to do some algebraic manipulation because this 70 is going to come into play. How do I want to write this? Oops. So it says that the acceleration due to gravity at height h equals 70%, so 0.7 of the value at the Earth's surface, which is the normal value. So I can just go ahead and manipulate this to get that. And ultimately, that's what we need to end up with. So the ratio of this to this is that. All right. So I am going to take, so I'm going to rewrite this, and you'll see why in a second. I'm just going to multiply both sides. Let me see. Let me do this instead. Let me rewrite it. So I'm going to multiply both sides by r squared because I'm about to make a substitution. R squared. This cancels. This cancels. You have r squared g equals gm. And then what is gm? Oops. what is GM? Or I can take this expression for GM and plug it back in here. So that's what I'm going to do. We'll write it in this color. So just do a quick replacement. G R squared R plus H. I mean, multiplication is commutative in this case. Yes.
Just answer your question. I told Ms. Because about this. I had an excuse to absence for last Wednesday. We had turned in the homework. Would it be okay if I emailed you that by this evening?
Yeah, that'll be fine.
Okay, thanks.
Okay. Email me that too.
Okay, I will.
Let's see. Okay, so that's equal to GH. And then, again, I'm looking for this. And so how do I can I somehow turn this into that? What do I need to do? Say it again? Yeah, yeah. So let's see, how do I want to notate that? And then divide both sides by G. To get two nice ratios, actually, or nice ratio like expressions. And there we go. And what is this? 0.7. Now we already know what R is. In this case, R is the same as, so capital R, they use capital R, I use lowercase r, so that's fine. And we just want to find out what the height is, so let me go ahead and rewrite that. Let's see. So you plug in the numbers, plug in the numbers. 400 squared, 6,400 plus H squared equals 0.7. And then, you can multiply. Well, I'll go ahead and do that actually. You can multiply both sides by this expression. 6,400 squared equals 0.7. 6,400 plus H squared, and then just proceed to, do the algebraic manipulation, which I won't necessarily do here. He gives a kind of interesting expression for it. He manipulates it that way, but it's all the same thing. I'm not quite sure why he divided this inside expression by R squared, basically, but you can do that. But it doesn't matter, just however you get to the answer. Let's see. Let me put this in a nice algebraic form, and then I may ask one of you to calculate it for me. After you divide by 7, yeah. So I'm going to skip a whole bunch of steps here, but make sure I said that. Okay. That should be the expression for the final answer. Does anybody feel like putting that in their calculator?
I think it's 1.24 times 10 to the 3. Or it's 1,249.46. Is it?
And sure enough, yes.
Yeah.
Good. Very good. All right. Any questions on that one? Okay. Like I say, it's a lot of algebraic manipulation. All right. So copy. And then let me see. The last one I'm going to go through. With this one, let's see. Hang on. The first three parts are actually pretty easy. Okay, hang on. Trying to think of what I want to go over here. I guess we'll go ahead and do A, B, and C. Can you all stay during lab time? I mean, I won't push it too far into lab time, but okay. So let me do this and then do the last one, and then that'll be it. And then, like I say, I have homework to hand back. So I have homework 4 and exam 3 corrections if you turn them in. So. All right. Okay, let's just go over a quick example before we, well, let me go ahead and copy. Let's see. We'll do parts A, B, and C. A, B, and C. Okay. Okay, so the same thing, we're just going to do a quick review here. The same thing applies for sine functions. So we've got, what do they usually call that? Oh, omega. T plus something. And phi is what that is. So we'll just identify each of the parts. That's basically the key of this one. You also need to figure out the frequency from this. Now A is very simple. It's the easiest one to identify. So it's basically how far out the sine or cosine wave goes, otherwise known as what? Well, it starts with an A. So the, what? Yeah, that's it. Good. Yeah, amplitude. And then the other ones get kind of tricky. This one we wouldn't actually need for this problem, but it is. So basically, whenever you add something to the input, it means that the wave reaches that, or the amplitude reaches that point a little early. So that's now, oops. Not yet, not the shift phase, but the phase shift. So it throws off things a little bit, it shifts it. And what's kind of counterintuitive and just kind of, because like I say, this causes I guess the X to reach somewhere a little earlier than expected. So if this is positive, then the curve shifts back. If it's negative, then the curve shifts forward. So that's kind of, just kind of a side thing there. And then here, we've got let's see, that's angular frequency, I think. Angular frequency. And this one will actually come up in this problem. Now we can also write the angular frequency as 2 pi divided by the period. And so that's what that's going to be. Huh?
What is the period?
So the period is how long it takes the sign to go through a full cycle.
Oh, yeah.
So basically, let's see. So it's kind of like, let's write it in a different color. Yeah, that's fine. Okay, so from here to here is the period. Hang on. The period. Now the frequency is 1 over the period. Just the regular frequency. Let's see. So period, let me see, I'll notate as T. No, let's just not do that. So the frequency.
What is
So that's usually, good question, actually. Yeah. What absolute value? What do you mean? Subscript. Let me see. Or
like capital. What's the opposite of capital?
oh yeah, lowercase.
Lowercase.
Yeah.
So it's just lowercase.
Yeah. In this case, this is what he uses. Now frequency is equal to. Hang on. Frequency is equal to 1 over the period, which is notated in T. Because period is measured in seconds. So it's kind of like a time, and then frequency is F. So yeah, and that's kind of all I'll go over in that part. Yeah, this will make conceptual, this problem. Now, this is my position. Let's say, okay. Let me see. How do I want to do this? So let's say that I have a position function. And I could put displacement, but let's put position instead. Okay. Okay, conceptual question here. So I have a position function, f of x, let's say. I want to find the velocity. Can I do that with this?
Yes.
How so? Yeah.
Because the derivative position is below.
There we go. Very good. Excellent. Okay, if I want to find acceleration, how do I get that?
The derivative of velocity.
Right. So second derivative of position, derivative of the derivative. Good. So then, because basically these two, that's what they're asking. So let's see. And in this case, let's just call this f of t. I'm trying to think, do we need to do this? Yeah, that'll be fine. That doesn't even look like anything though. F of t, oops. F of t. Okay, so position in this case is 4 cosine of 1.33 plus, oh, I'm sorry, t, I can't forget the t plus pi over 5. So if that's position, then what would the velocity be?
The derivative of that, which is 4. What is the derivative of sine?
Yeah, that's so derivative of cosine is what? Actually, quiz time, hang on.
Negative sine? For sine?
Well, hang on.
I don't know. It's like a trick.
We'll do quiz time. Let's see. Derivative of, let's say, cosine of x is, let's see, no, come on. Hang on, I need to make the font bigger. Okay, let's see. Let's see. Okay, and then delete the rest of that. Hang on. Okay, A, B, or C? What do we think? So who says A? Okay, so A, nobody for A. Anybody for B? Anyone for C? Okay, yes. Now, by the way, what is the derivative of sine? Not negative? Is it negative?
No.
Yes, that's right. Yeah. So yeah, just remember those. So when you're going from cosine to sine, or really anything to anything, I think it's negative. And then from sine to the stuff, that's when it's not negative.
It is.
Yeah, integration. Yeah, just think about it in reverse. Yeah. Yeah. Let's see. So we'll say that is correct.
So I got 100.
Yeah, on the quiz, yeah. Your extra credit. All right. So yeah, let me write this. So then we have 4. I'll go ahead and put negative out here. Sine of. Oh, okay. Oh yeah. Let's see. I wish I could. Let me see. I don't think let's see. Do we need to scan this in? I think you can find.
You can probably find all this on the internet.
Yeah, let me see. Yeah, let's see. Can that be seen? So here, let me see, where is it? Well, nobody could, let me see. I would have to switch the camera. Thank you, though. Hang on, let me see. Let me switch the camera. Let me see if I can.
If it would work, I could scan it at home and send you a PDF copy.
Let's see. Where am I? Yeah, so there we go. So
No, backwards.
I think when it records, it reverses it. Where am I? Okay, there we go. So there we go. And then you have, why did they put cosine over there? So there we go. So you got those. Cotangent gives you the negative. Well, that's cosecant anyway. So
Yeah, that has
Well.
all of them.
let's see. Secant does not give you negative. Cosecant does give you negative. Tangent does not. Where's cotangent? Trying to read these backwards. Yeah, there we go. So yeah. All right. Thanks. Yeah, so just make sure you know your integrals, because you never really know when you might drop one in there. All right, let me see. Let me share my screen again. All right, so we got that. All right. Okay. Let's see. Actually, let's switch the camera back. Oh yeah, camera was on me. All right. All right. So we've got 1.33 t. But then I multiply by the derivative of the inside function, so that gives me 1.33. So pretty basic on that one. Let's see, where does he get that? Okay, he multiplies. So he multiplies this one, and that's how it, so he gets 5.32. And then we take the derivative of, again, so derivative of sine is cosine, but I still have a negative, so I'll just leave that out there. I don't have to worry about negative, and then 1.33 t plus pi over 5 times this again, but I'll just go ahead and write this as 1.33 squared. So yeah, so that's basically all of these. So any questions on that? Like I say, I kind of wanted to make it a little general, a little conceptual. Question?
So what is this? 1.33?
Yeah, and the notation's a little, so basically I'm multiplying this sine function by this. And, you know, same here, I'm multiplying this by that. I got this because I had to take the derivative of the inside function. So after I took the derivative of cosine.
The t, that's why. Okay.
Yeah.
Yeah.
Then we have a constant here. I don't even worry about that. And apparently my battery's going down a little bit. I think we can still make it. Okay, so we got that. And then last one I'm going to go over is going to be one about deformation, and it's short. Which, by the way, I meant to mention this, but deformation may come up in statics. I'm not sure. I remember when I was taking courses, deformation came up a lot, where you had I think it was called statics, where, you know, you bend something until, like I could take that slinky over there and stretch it. And maybe you all have done this, you know, stretch the slinky until, you know, the point where it stretches so much that it can no longer, you know, go back to its nice. So, I mean, don't do it now, but yeah. But yeah, because I remember when I was younger, I used to always do that and ruin my slinkies. Yeah, it happens. Yeah, we used to have like the rainbow colored ones that we get. Yeah. So that may come up again, the deformation thing. All right, so I got that. Let's go ahead and delete. And then let's see, how do I want to do this? We may just go through this. Let me just go ahead and put the PowerPoint up here. I don't really have to write this one up here. Okay, so we'll skip all this. Okay, so I'll just basically go through this. So I almost don't need to go over this. So you have basically, okay, well, there's one thing I want to go over here on how he gets this. So the cross-sectional area is, this is the expression he gets from it. It looks a little confusing. Let me just quickly show where he gets that. So area, really quickly. So area of a circle is what? Yeah, I think.
4 no. It's pi
Yeah, there we go. Pi r squared. So that's radius. What is radius? It is equal to the diameter cut in half, just by definition. Okay, so let me take this, because we're given diameter, we're not giving radius. And so, that's why he wants to put in this expression. So take this, I almost want to write that in a different color. I don't really have to, but let's just do it. So R equals 1 over the, diameter, half of the diameter. Take that, put that here, and we get pi times this expression, d over 2 squared. And then if I multiply all that out, I've got pi here. I've got d squared here. I've got 2 squared, which is what? 2 squared. Yeah. So that's how he gets that. And then I can just kind of, pull out the 1/4. How does he write it? Because I want to write it in his form. Yeah, there we go. So there we go. So that's how he gets that part. So if you're given the diameter, if you're given the diameter, you can go through the derivation. It's probably more trouble than it's worth on an exam. Just, cut the diameter in half, use this, it'll be easier. But this is what he does, and that's how you get to that whole thing. So then he uses like the Flay formula or whatever. So you need, I think, Young's modulus. You need how much the wire stretches. You need the force exerted on there. And then you need the cross-sectional area. And you just plug in the numbers, and that's it. Stress and strain, you just use those formulas. So that's probably where I'm going to leave it. And like I say, for the other ones, he does explain pretty well, I think. So feel free to look at those. And I'll email this out later on today, or maybe right after this. So, that's all I have for this. Are there any questions or anything from anybody? Like I say, afterwards, if you want help with your grades, I can help with that. Let's see. Yeah, there we go.
Are you going to send out the PowerPoint, right?
Yes. Yeah, that I'm going to send out. Video, hopefully I'll send out. What else do I need to send out? Homework 4, I think, solutions, which, by the way, let's see. Well, yeah, I was pretty liberal with the bonus points. On 5, I think it was problem 5. If you got it wrong, I think I only took off 2 points because it was kind of a tricky one. So I was kind of confused about that. And I kept seeing the same answer, the same, not quite right answer. So maybe something was amiss. But I'll send you out the solutions that he has as well. Oh yeah. Yeah, in problem 2, I think there was a decimal misplacement. So if you, trying to think, if you use 6 or 60 seconds, I gave you full points. I think that's how I did it. So yeah. Any other questions?
What question is it gonna be?
On the final, will probably be 5. I mean, it won't. Well, let's see, because it's just going to be a normal test. I think it's going to be 5. So yeah, like it normally is. Now, keep in mind. Obviously, there will be no time for test corrections. We will have the same setup that we usually do. Textbook or textbook notes, PowerPoints. So that'll be fine. But just realize that there will be no time for correction after. So just kind of study up, and I'll try to be kind of generous with the grading and stuff. So
We have access to all tools.
yes, yeah.
So what are you doing? Make things more specific. Are you just taking the final exam 20 points out, merging it to the rest of the?
Yeah.
Well, then that means each category will count for 25 points instead of 25.
Well, no, for that, like I say, just the grade will be out of 80%, not 100%. That's just the easiest way to look
So
at it.
80% would be a
Yes, if you get 80%, yeah,
So
that's
actually,
the way to put it.
punished towards us, so it would be a lower points to pull
Not this. Well, I guess each point will count as the same, or count a little more. Bless you.
Yeah, each point's gonna be 20% worth 20%.
Bless you.
Was.
Is something like. Well, let me see. What is that?
Changes the weight of all the tests.
Yeah, the weight's heavier on everything. Don't put it that way.
Yeah, but at least the final doesn't kill you. If you do bad on the final, then it doesn't kill you as much, if you know what I mean. So, you know what I mean?
Yeah, I know what you mean.
So,
It'll come out exactly the same.
yeah. So let me see. It'll be 12% more. Or no, 25% more, I think. Each point will be. Right, because
Work
yeah.
that, I could make 80 cents for $1. I'd be rich.
But yeah.
So, what about we're still doing the 10 bonus points for study sessions?
Oh, yes, yeah. Yes, Stephanie has been getting that together. And I'm also able to kind of give input to.
So I've been going to Professor Dan every Saturday, except
Okay.
for the Thanksgiving weekend. No one was here.
Yeah, no, that's fine. That's fine. And yeah, I think we have a list of that. I'm not the main go-to on that list, but I've been compiling a list of my own for those of you who have attended mine. And like I say, I kind of am able to. If I've seen you working, hard in this class, then I can kind of, give maybe a little bit of recommendation to, because it's the professor who will be giving the final grades, but I can kind of, give. So just
His
keep that in mind.
grading's been fine.
His,
He's the one who's grading all the lab reports, right?
yes, yeah.
Yeah.
Oh, okay, okay.
I'm not saying he'll be generous on anything else, but he's been generous at least to me on those.
Okay. Well,
I
good.
think all he really cares about is formatting, actually doing the stuff he does.
Okay.
Doesn't care if it's wrong or not.
Yeah, I don't really know how you would grade a lab, to be honest with you. But well, all right. Let me go ahead and stop the. Let me stop the recording.